again? Yes, I can. I love it. Okay, so don't worry, by the way, this session is shorter than other sessions. So I just need to tell you what to do and you will be dismissed. So back to this one. Okay. All right. Anyway, so back to this one, you can see that I have 2 point-like sources, both positive. And in this case, you have 2 point-like charges that are opposite. What you see here is not E1, neither E2. It's the combination of E1 plus E2. So this is E total. So this weird shape or behavior is not E1, neither E2. It's the resultant field. Okay? And I'm sure you already saw that back in grade 11. I don't know if you remember, right? Yes? All right. In this case, I'm going to show you the case where you have a negative source. It's a source that is negative. It could be an ion like SO42 minus. And let's say I put very close to it a proton at point A. What happens to my proton? And when I mean by happens, like I'm discussing the motion of it. So what happens to my proton if I place it at point A? So Dana is saying attraction.
Yes, the positive charge will be attracted to the negative charge.
All right.
So the proton will move closer to the negative.
Okay, so basically I can say that due to the attraction between a positive charge and a negative charge, the proton will move towards the negative charge. Or I can simply say a proton will feel a force parallel to the electric field in the same direction due to F equals Q times E. So F and E will have the same direction if Q test is positive. So the proton will move in this direction. So if I put the proton at B, it will move from B to C, right? Yeah? Okay, so now I want people to try to define what is potential at B. Yeah, potential at B. And what is potential at C, and maybe compare them. Can I say that VB is greater or less than VC? That's the question. So please speak up. How do you think? Yeah. Say it again.
I mean, VB greater.
VB is greater than VC. Do you guys agree with Joe?
Yes, I think so.
All right, I know the closer I am to the negative source, the potential it gets really small. So I know for a fact that VB is greater than VC. Now the question is, the proton will move from high potential to low potential or low potential to high potential?
In this case, fruit from high to low.
Okay, the proton always moves from high potential to low potential. Okay, some students would say towards to low potential. Some students would say towards the positive, towards the negative, I mean. You can see it low potential and high potential. So we all agree on the fact that potential at B is bigger than potential at C, or at least B and C, they have different potential. What do you call, what other name do you give for potential difference? Or how do you measure a potential difference? Do you know of any measuring tool? Yeah, we call it voltage, Joe. A voltmeter, Joe. Thank you so much. So we are in the lab and the only tool we've got is a voltmeter. So we're gonna use a voltmeter to measure a certain potential difference. We won't be able to measure any electric field. We don't have any measuring tool for the electric field. So now my question is for anybody who knows the answer. What's the potential difference between A and B? Or who've got more potential, A or B? They are at the same distance away.
It's equipotential surface.
So Dana and Ryan and Jana are saying they have the same potential. So A and B, yes, they are at the same distance away from the charge. And since the potential is inversely proportional to the distance, D, they have the same potential, meaning that all the points that belong to this red line, they do belong to the same equipotential line because they have the same potential. And if I get a voltmeter and measure the voltage between this point and this point, or between A and B, what do I get? Zero, Dana. Yes, excellent. So the potential difference between A and B is actually zero. All right, and we're gonna do this in the lab. These are different shapes to show you equipotential lines. So the blue lines are the electric field lines, and the black dotted lines are the equipotential lines. In this case, you have two charges of the same nature. In this case, you have a surface that is negatively charged and a point-like charge. You see the electric field lines and the equipotential lines, and here as well. Okay? All right. This is also an example that shows you equipotential lines. This line is called the 3 kilovolt line, and this line is called the 1 kilovolt line. It means all the points that are on this line, they have the same potential, or the potential difference between them is zero. 1000 volt means with respect to this reference, so V equals 0 is the reference in this case. So if I measure between this line and this line, I get 1000 volt. But if I measure between this point and this point, I should get 0. You see what I mean? All right, and these are different shapes, and the curvature of which is very important. So that's it for our starting point for the lab. You see that the theory was displayed in a very descriptive manner, and all the theory is like grade 11 level. I know in the course you go more deep and more advanced, and the lab itself is gonna be descriptive, and you will have a qualitative approach. Now let me show you the lab report and then the recorded session of the experiment itself, okay? The lab report is in your manual, and I'm gonna definitely split the manual into different chapters. Let me show you chapter 1 or lab 1 and what you're supposed to be doing. So this is the manual section. You see experiment 1. You see you don't have a lot of equations. Basically, it's a descriptive approach. And I love this one. I wrote it. It's an analogy between the gravitational and the electric equipotential and forces. Yes, Jean. So the lab report is gonna be individual for many reasons. It's good and bad in a way. It's good because you can focus on your own schedule and your own agenda and submit on time. It's bad because maybe you will have more work to do, but since the lab reports have been modified, I hope that not all the lab reports are gonna be lengthy. Maybe one or two, but not all of them. And at least I can focus with you. So if you have any questions, so it's gonna be individual, okay? So each on his own, I'm gonna be the partner of everyone if you need me to. So going back to the analogy between gravitational and electric field, the potential in the case of electric field is gonna be the height in the case of gravitational field. So you see this mountain and the different height, and you would see, this is like viewed from above, and you see on the topological map, the different heights or the different equipotential or equigravitational line. Try to read it and see if you can see a certain analogy between gravity and electric fields. Now the procedure I'm gonna show you in the video. So you watch the video for the procedure and you read it again. And these are some notes you need to follow. Hopefully if I see you in October, I can offer you few minutes to try to create your own map. I think it's very beneficial for lab 1 because lab 1 is all descriptive. So it's good if you do your own map. Although I'm gonna share my personal map with you for you to be able to do your lab report this week. This is the lab report. Question number 1, map the equipotential lines on a graph. I'm gonna do this and I'm gonna send you number 1. You do number 2, then 3, and answer all the questions. A lot of the questions are theoretical questions. A lot of these questions are related to your map. So you're gonna draw, you're gonna answer. Although most of it is gonna be descriptive, like you draw and write. There's no calculation involved, no data analysis involved. So that's for lab 1 only. Later on, it's gonna be different. And that will be it. So you see the lab report is not too long. Now I think we can move to the procedure unless you have a question. No question? Now those labs were shared on YouTube, so I'm not gonna send you the video. I'm gonna send you the YouTube link and we're gonna watch it together. As you can see, you have two videos. The reason is I didn't want you to have one long video. It's frustrating. At least you can watch the experimental the list of equipment alone and then the procedure alone. Okay. Hello everyone, welcome to the first experiment we have for Physics 306. It's called electric field mapping or equipotential lines. All right, so let me get the camera closer to show you the different equipment we have. All right, so the equipment needed, you need a multimeter. This is the test multimeter I will be using on the scale volts. You need 4 banana wires. So you can see 2 banana wires already attached to your power supply and another 2 banana wires that I will be using for my multimeter. Right? By the way, this is the power supply because you won't be able to see it. It's a DC power supply. You can control the current and the voltage as you may. You have a positive terminal and a negative terminal, the power on-off button, and it's connected to the mains. What else? This is a board, it's a cork board on which I'll be using a conductive paper. This conductive paper is supposed to be brand new, so it shouldn't be poked anywhere, and this is the case. So I'm gonna take... So most of the papers you have are already poked with this, the students poked them to do the experiment. So in a way they are destroyed. So we need to start with a brand new one. The conductive paper. So that was the equipment needed. Now the procedure. I'm gonna place the conductive paper on top of the board. I need to make sure I have conductive pins attached to my wires. Okay. I'm gonna poke the paper rigidly at the extremities of the paper. All right, so this was the first part of the lab. Now let me get us the second part that would continue explaining the procedure. One pin is connected to the red banana wire that goes into the minus terminal, and one pin is connected to the blue banana wire that goes into the positive terminal. The power supply is off, so there's no potential difference between these two points. But when I put the power supply on and I see a 20 volts displayed on the screen, I would know that I just created 2 point-like charges. The potential difference between these 2 point charges is 20 volts. Now my job is to use the voltmeter, the multimeter on volts, to be able to try to do some measurements. I will use my voltmeter on the scale 20 volts because 20 volts will give me 2 decimals. I will not be measuring voltages more than 20 volts, more than 2 volts too. So I can simply use 2 volts as well. But 3 decimals for me is a lot of precision and I don't need this, knowing that the experiment is not super precise. So a scale of 20 volts. Ahad, please mute your microphone, okay? Or measurements of 2 decimals are enough. I'm going to take these wires, the blue and the red one, plug them into the COM and the V plugs. And I'm going to use, I will put this to the camera, hopefully you can see it. Okay. And I'm going to be measuring the voltage or the potential difference across my paper. If I measure the pins, the potential difference across the pins, I should get something very close to 20, and I'm not because my power supply is off. I will put my power supply on and I can see a measurement very close to 19.9 volts, which makes sense because these are the terminals of my power supply. Now, if I measure the potential difference across two different points on the paper, I can see that it's a non-zero measurement, which means these 2 points do not belong to the same equipotential lines. Remember, points do belong to the same equipotential lines in case they have the same potential, therefore the potential difference is zero. Now my job is to find equipotential lines and to be able to map them. So I'm supposed to find 2 points or many points belonging to the same equipotential line, therefore having the same potential, therefore having a potential difference equal to zero. I'm gonna start with my red terminal being my reference exactly in the middle of the paper, and I'm gonna try this point. Does it give me zero? No. I will move it a little bit to the left to get zero. I found my zero. I write down the coordinates of this point. So before I start doing the map, I should prepare a paper very similar to the black paper, like a regular paper. Make sure to have the coordinates. Every box is 1 centimeter and the smallest subdivision is 1 centimeter, which means the precision is very low. That's why I didn't need a high precision for my voltmeter. And every time I find a point on my equipotential line, I would mark it on the white paper, you see? I think I don't need to write the coordinates. It's a waste of time. Just mark it on the white paper. And this is what I did, and this is what I'll be sharing with you. Now the blue terminal 1 centimeter up. Is it a zero? No. I will move it a little bit to the left. Bingo, I got zero. I will mark my coordinates. And so on and so forth. I'm gonna find all the zeros, mark them on a different paper where I can see the coordinates. It will be a duplicate of this conductor paper. Done with my first line. Now I will. So you're not supposed to be moving your reference until you finish the line. And once you finish the first equipotential line, you would move your reference 1 centimeter to the left and start drawing the next line. By the way, this is what you're supposed to be getting. I shouldn't be closing all these files because we keep on using them. So what you will get is the following. Wait a second. You will get maybe this one. Okay, this one. Aren't you having 2 pins of opposite charge, plus and minus? The potential difference between these two is 20 volt, which means you can have a potential here of negative 10 volts and here positive 10 volts, as long as you have a difference of 20 volts. You should get black lines very similar to those dotted lines. So the one in the middle is gonna be straight. And as you get closer to the source, you will see some curvature. And this is what I'm gonna show you in the video here. A curvature will start showing up. Listen up. Actually, move my reference 1 centimeter to the left and do the same thing again, trying to find my zeros. 1 centimeter up, 1 centimeter up at a time. Move the reference until I get very close to the source where I can see that a point just above the reference will not give you zero at all. It will give you a value very far away from zero. This is where you're supposed to be moving your blue banana wire to the left and find this zero that I'm not being able to find. Where is that zero? Okay, let me try again. Okay, I just... So do you see, I was actually getting a zero, but I was moving from negative to positive, but since my head is away from the screen, I did not see that. Check it out. I think my paper is broken, that's why it's giving me weird results. So smaller to zero, this is the zero. To zero. I had to move 2 centimeters to the left. Okay, you see the fluctuation to get a zero value, which means my line will end up being curved as I get closer to the source. Okay, so I move my reference 1 centimeter at a time, my blue terminal up and down to find the zero values for the potential difference. Well, then I would use my reference to move it 1 centimeter at a time to the right side and be able to find the different value. So that's it. I will share with you the results of my map. It will be a map of the different equipotential lines created by 2-point-like charges of opposite magnitude. All right, so concerning the procedure, usually I find it very difficult to explain to the students how to proceed and create their own map. I don't know if in this video it was clear or not. Please let me know if you have questions. You guys are fine?
Yes, but Dr. video, right?
Yes, the video has to be shared with you. That's for,
okay.
And the recording as well. And the map, because you cannot do the map from the video. I need to give you my own map and you answer the questions accordingly. Okay?
Okay.
Any other question? And you know where to submit. Ahad, you just joined. Do you have questions? Otherwise, you can watch the recorded video and the video for the experiment and you let me know, okay? So try to finish your work before the end of the week. Don't wait until Monday. And all right, Ahad. So, and please, you can at any moment send me an email if you do have questions, okay? I did not understand your question. Are we gonna use a two paper, the black and the white? All right, so the black usually stays in the lab, right? So it stays in the lab and we don't actually write on it. We only do the experiment on it, Jean. So usually I write all my points on the white paper that is a duplicate of the black, and I draw the equipotential lines on the white paper, and I take a picture of the white paper and give it to you. So Jean, you will get a picture of what's written on the white paper, and the black paper will be untouched. You see, I already poked it twice, okay? But that will be it. For the next team, let's say another team is coming to the lab and they want to do the experiment, they can still poke 1 centimeter closer to the center and do the experiment between the two sources. So we can still use it a bit, maybe 3 times before we throw it, but no, we're one paper is for the experiment and the white one is to draw the equipotential lines. Did I answer your question, Jean? Okay, awesome. Are we good? If you guys have no questions, you are dismissed. And if you have any question, you can stay behind or email it to me if you want. Okay? Perfect. All right, enjoy your day.
Thank you very much, Dr.
Thank you.
Thank you.
Bye, doctor.
Bye.
See you next week.
Bye.